So we were discussing about different properties of a magnetic material. Maybe if I go back one step. So one parameter which is always associated with ferromagnets or magnetism is Curie temperature. So what is Curie temperature? So like when you look at the variation of magnetization M as a function of temperature. So at certain temperature value, the magnetization will become zero. And then above that temperature, it is paramagnetic. And below this temperature, it is ferromagnetic. So this temperature is called as Curie temperature. And of course, it was observed or found by Pierre Curie. So experimentally, he measured many materials, ferromagnetic materials, and observed this Curie temperature. So, for example, here in nickel, so this is around 628 Kelvin. Okay, for iron, it is like more than 1,000 Kelvin, and so on. So again, for different materials, the Curie temperature is different. And so when we talk about magnetic materials, if you are talking about applications, so first thing you should know whether the material is ferromagnetic at the temperature, like at which temperature you want to work. So if you are working at room temperature, so the material has to be ferromagnetic at room temperature. So definitely nickel, iron, cobalt are all these are or they are alloys. So they are all ferromagnetic at room temperature. So that's why they are used. There are many materials which are actually ferromagnetic but at low temperature. So if you go to like below 100 Kelvin, so even below 5 Kelvin, so many materials are actually ferromagnetic as well, but they are uh, not, let's say, so useful for applications. So in the last class also there was question like what is coercivity. So coercivity, as I explained, so it is just a field value. So when in the y-axis, what you see is the value of the coercivity. So it varies from 10 to the power minus 1 ampere per meter up to 10 to the power 7 ampere per meter. And then depending on the value of the coercivity, so you can divide the material as a hard magnetic material or a soft magnetic material. And so hard magnetic material will have higher coercivity, or the coercive field will be high. So the order, you can look at the order of difference. No, for soft magnetic material is 10 to the power minus 1, and here it is 10 to the power even 10 to the power 6, 10 to the power 7 of that order. So there's a huge difference in this order. And the higher the coercivity, it is difficult to demagnetize that. So demagnetizing means, so you make the magnetization zero or completely vanish. So the total magnetization will vanish. And then in this case, for hard magnet, it is difficult, and therefore a lot of material research is going on how to increase coercivity for many applications. Okay, and for many other applications, you need low coercivity or no coercivity at all. Uh, for example, when you are using it in transformers, so both kind of materials are necessary for applications. And this is actually how the development in research, material research, led to much better or efficient materials with high coercivity. Like you can, so this shows like how you can really control coercivity, uh, and you can have a control and mastery, how you can make a material which is with a high coercivity or low coercivity. Another property which often like engineers you might not see most often, that is called anisotropy, magnetic anisotropy. So magnetic anisotropy is actually, so anisotropy means any material properties. When we talk about any magnetic, any material properties. So, so if I take, let's say for density, for example. So density, I expect that it will be isotropic in a material. So wherever I go in a material, so the density will be the same. Uh, or if I go to any point in a material, so maybe the the value of the resistivity or the resistance will be the same. It may not, it should not uh, change. Uh, that is like an isotropic property. So it is the material properties is exactly the same wherever you go in the material. So it doesn't matter. So like you are at the edge of the sample or you are like along any direction you go, so the properties will be exactly the same. But anisotropy means certain properties will exist only along certain axis. So in a axis, so normally you talk about x, y, z axis. So if you take a rectangular shape, that is obviously you can define it well. But if you take ellipsoidal kind of shape, so you have or ellipsoid or ellipse like, so you have long axis and short axis and so on. So here in many magnetic materials, so you it is observed that the magnetization. So magnetization is a vector. So if it is an isotropic system, so the vector is supposed to point in any direction. It is fine, doesn't matter. But most of the magnetic materials, you will actually see that magnetization will lie only along certain axis in that material, and that gives rise to anisotropy. Okay, so that is known as magnetic anisotropy, which is like almost, it's like an intrinsic property of the material. So depending on the material or the structure of the material, so structure means how the atoms are arranged in the material. So if you take iron or if you take cobalt, so they have certain crystal structure. Okay, so the crystal structure means how the atoms are arranged in a regular pattern, uh, and that leads to, so and when they are regularly ordered, so this gives rise to that magnetization will only align or stay along certain axis. So either it will be along so for simplicity, I am saying it could be maybe along z-axis or could be y-axis, and that preferred axis is normally called as EG-axis, and that is always like a, also associated with the energy of this uh, nature, this Ku sine square theta. Uh, and when you apply, so typically the magnetization, this vector would prefer to stay along this dotted line that is called as EG axis in a magnetic material. But when you apply a magnetic field, so this is another vector, right? And so magnetization will have a resultant, it's like a resultant vector. So of this EG axis, this vector and this vector, and then it will make certain angle theta with your EG axis. And that is typically true for most of the materials. So we may not go into the detail of anisotropy, but I want to mention it that many materials, this magnetic anisotropy is one intrinsic property which plays a major role in determining how good is the material. So this, in fact, this anisotropy determines the coercivity indirectly. So if you actually look at hard magnetic materials where coercivity is large, so in that case anisotropy will be also large. Okay, so that's why if anisotropy is large, so that means it is difficult to demagnetize it, and that's why the coercivity field or the coercive field will be large. So similarly for soft material, anisotropy will be small. Even for many soft materials, there is no anisotropy actually. So the magnetic material is isotropic. Yeah, yes.
So in the previous slide, why you use the term easy access? In,
EG axis, why? Because we want to, so we say it is easy access because magnetization. So if I say, if I remove the magnetic field, for example, so there is no magnetic field. Okay. So in that case, magnetization will stay along this axis. So that means it is easy for the material to have the magnetization along this axis. So similarly, there will be a hard axis, which will be perpendicular to this easy axis. So hard axis means magnetization will never prefer to stay along the hard axis, which is 90 degrees to this easy axis. So if my easy axis is along Z, and if I have no magnetic field, so in that, so if I take example, let's say cobalt. Okay, so cobalt is a hexagonal structure, crystal structure. So if you imagine a hexagon, so you have this hexagonal side and then the z-axis. So I say this is the elongated axis. So you have hexagonal plates, and then along the c-axis or along the z-axis, so it is that's a longer axis. Okay, so in cobalt, magnetization normally prefers, or the easy axis is this z-axis, which is perpendicular to your hexagonal plane. So that means if you do not apply any magnetic field in a cobalt, so magnetization will stay along that z-axis. Okay, so it will never stay along this x and y, which is in the plane of the hexagon. Okay, and that's why, and that axis will be called, this hexagonal plane will be called a hard axis plane. So the magnetization will never do that. But if you apply now a magnetic field, a strong magnetic field, so really strong means maybe a few hundred or few tens of Tesla. So Tesla is like 1 unit of magnetic field. So if you apply a strong enough field, for example 5 Tesla or 6 Tesla magnetic field, so you can actually move the magnetization to the hard axis. That is possible. Okay, but typically if you do not apply any magnetic field, so magnetization will stay along the EG axis or this axis, anisotropic axis. That's why this is called EG axis, and EG means it is easy to magnetize along that axis. Okay, is it clear?
Okay, sir.
Yes. No, in isotropic material, you will have no EG or hard axis. So isotropic means all axes are EG basically. So you can magnetize it in any direction. So you can magnetize along X, Y, Z, or anything, any angle between X, Y. So it does not matter. Okay. So all directions will be easy in that case. Yeah. So another parameter is susceptibility. Okay, so susceptibility is defined like it's a response to the magnetic field. So applied magnetic field H. So which in this case is so this is the external field H, and we have a response to that, which is magnetization. So the ratio of that is M by H. So in many times you will see that instead of chi, people use mu, which is a permeability, so which is a ratio of B by H, the magnetic induction. Okay, and what is interesting about the susceptibility is actually one of the parameters which will define or decide whether the, or which shows whether the material is paramagnetic or diamagnetic or ferromagnetic. So we will see how the susceptibility actually can be used to distinguish between these materials, different magnetic uh, ordering. Okay, so the temperature dependence is given by this Curie law, so which is 1 over T. The susceptibility is 1 over T. C is a constant. But many ferromagnets or even many paramagnets also, you will see that this is not this kind of behavior, Curie law, but they follow this Curie-Weiss law. So which is given by C T by Tc. So Tc is again basically the critical temperature or the Curie temperature. Okay, so we'll see in detail in maybe next lecture or after 2 lectures. Okay, so here I just keep these slides like for your references so that you know what are the different applications of magnetic materials in different areas. So permanent magnet, soft magnet, and magnetic recording. So this is a like a distribution of like how much magnetic materials are being used in different applications. This is again the same, but with a detailed different kinds of material. So, for example, in the hard magnetic material, you have materials known as ferrites. So, this neodymium iron boron we discussed. This is like a permanent magnet. So, there is also samarium cobalt. So, this is one another like samarium is again from this lanthanide series, and cobalt again and magnetic material. So iron of course is there. So now when you see here, this is hard magnetic materials, and in this yeah, so these are all magnetic recording materials which are used in magnetic recording. So in your hard disk drive. And then these are the materials which are used in as soft materials, mostly in transformers for high frequency applications. Okay. Yeah, another thing here, this is again the soft materials are amorphous. Mostly amorphous materials will be soft materials. And again, so here one section is soft ferrite, there is hard ferrite. Okay, so there are two different kinds of ferrite materials as well. So in electrical engineering, we'll come across this ferrites, which are used in a permanent magnet, also ferrite core, which is also used in transformers. So if you come across something, anything in a transformer or in any AC application, it is always will be a soft ferrite. Okay, so that means it will always have a low coercivity. Yeah, this is again a picture which says how the development in material led to this. So soft, basically for soft magnetic materials. So how the core loss. So the loss is measured in watt per kilogram, and in the beginning the loss was quite a lot, but nowadays you have really minimized a loss even 100 times less. But still, people are working on how to develop new materials where the loss will be even lower. So this is again another representation of hard magnetic material for permanent magnet. So as you can see, this BH max, so it is increasing. So if you go back to 1900, so this BH max was something around, let's say 40 kilojoule per meter cube. So the this is the SI unit, and this is basically your CGS unit. Uh, so both have exactly the same value. So one on this axis it is represented in CGS unit, and here on this side it is represented as a SI unit. And then now in 1980s, 1985, so this neodymium iron boron was synthesized, and then you could see the BH max or the energy product is quite high. So compared to what we had in 1900 to what we have in 2000, okay, and it is still like kind of going up, okay. People are adding different materials, combining. Uh, so you can take this and add, like we said, dysprosium you can add. So people are also adding or doping different elements to increase this value as well. Okay, so this is basically a summary of all magnetic materials what are being used uh, right now in the industries. So that actually summarizes all kinds of hard, soft, semi-hard or semi-soft materials, everything in this plot here. So what I want to say is this magnetism is for application. Okay, you are looking at materials which are this iron cobalt or some neodymium based or samarium cobalt based, or these different kinds of compounds you're making. But magnetism in general exists from an electron. So an electron is also magnetic, up to if you go to galaxies. Even galaxies are also, they are magnetic. So the magnetic field are of the order of like 10 to the power 12 Tesla. Okay, so most of the application what you are working on in this field, right? In engineers, that is what they use basically, from few nanometers up to few micron or maybe few centimeter. That is what the that kind of length scale in magnetism. That is what you might be working in future if you want. But magnetism can be explored in electrons, in atoms. You can manipulate that as well, and even you can look at the magnetism of galaxies. Okay, so magnetism is like huge in terms of scale. And in terms of the value of magnetic field, so if you look at your brain, so human brain has a magnetic field of almost like 1 femtotesla. So this is like 10 to the power minus 15 Tesla, okay, of that order, 10 to the power minus 15. And if you look at a galaxy, it's a magnetar, it's a star, so it has 10 to the power 12 Tesla. So the magnetic field, the strength of the magnetic field is also can be huge, no, I mean 10 to the power minus 15 Tesla to 10 to the power 12 Tesla. So for example, Earth's magnetic field is about 50 microtesla, okay. But in the laboratory, what you use is like maybe Helmholtz coils or this electromagnets. So something from a few millitesla up to few hundred or maybe few Tesla or 10 Tesla, something like that. So this is a superconducting magnet. So magnets which are made from superconductor. So this superconductivity we will discuss in the end, and then you'll see also this can also make a nice, really good magnets with huge magnetic field. So now even people can produce 15 Tesla, 20 Tesla magnetic field in the lab. I want to show you one video before we leave. I will start that video. Let me see. So, which will take us to the next class basically, or we will, yeah, this one. Okay. So what you see here is a frog, which is basically levitating uh, in a magnetic field. So this is a cricket, I think, or some insect, which is also levitating, and this is a water droplet of water, which is actually kind of levitating in a magnet. So it is almost like, I mean, if you look at the picture, you think it is something like there is no gravity there, but all these experiments were done on Earth, based here, without just using a strong magnet. So the question is, why do they levitate? Why they do not feel the gravity? Okay, so that will be our next topic in the next in the afternoon session. Okay.